Thank you, everybody. תודה לשתולים. So the title of my talk is Data Scientists Are From Mars, Software Engineers Are From Venus. I hope most of you know the book reference. A bit about me. I had the research department at Gong.io. I teach data science and machine learning at various institutes. I studied ecology. I studied biology. I'm not a software engineer, okay? And a lot of the things I'm saying now, and I show this, is in order for you to understand my point of view, not coming from a software development background, okay? So a less sexy title to the talk might be, how should software engineers and data scientists work together? But in order to actually answer that, we must first understand what a data scientist actually is, okay? And the best definition that I know of is that a data scientist is a data analyst working in Silicon Valley, okay? We're pretty advanced here in Israel, have a sparkling startup scene, so maybe in Israel as well. But seriously, we know of different positions. There's the data engineer and the data scientist. Are those two different positions? Or maybe this very commonly used Venn diagram that shows that claims that data science is the intersect of mathematics, domain expertise, but a lot of computer science is actually what needs to be used. Somehow we get a feeling that in order to be able to do all of those things and be good at all of those things, you have to be like a super developer. But maybe, you know, in practice, in real life, most of what you do is import keras and use existing frameworks and not really invent the wheel all over again, despite what others and you might think. Okay? So in order to discuss this, I first want to go over what we do at Gong.io and a special use case of one of the things we tackle. So for those of you that don't know, Gong.io is a pretty young startup, just 3 years old, but we're already at 150 employees. And we help companies improve their business conversation, focusing on sales calls. So think of a company, mostly B2B, selling to a different company. Okay? Gong automatically records, transcribes, and analyzes those sales calls, providing insights like top sales representatives talk more about the competition, but later in the call and only after they've talked about the value of the solution for a certain amount of time. Okay? We have large customers, large brands that use Gong already. We work on tons of data, and we have a pretty large research team of 10 researchers, in addition to the machine learning engineers team that work together with us. So when we have a call recorded in Gong, there are many, many different tasks that we have to perform on it. We have to identify the speakers in the call. We have to identify the language. If it's English, we'd use one version of the speech recognition engine. If it's French, we'd use another. Okay? We want to analyze what's going on in the video. Is it better to share your webcam when you're doing a sales call, or maybe to present a platform in a browser demo or a presentation? Okay? With Gong, we analyze all of those things. Once we have the transcript, we can detect the questions. Okay? Do top salespeople ask more questions or less questions? Okay? And then we analyze with a lot of NLP what's going on inside the conversation and eventually get to coaching and helping salespeople improve. And I want to take one use case and discuss this. And this use case is the Voiceprint Detection. Okay? So we want to identify the speaker in a call with little metadata, just using some Voiceprint model that we generate for this particular user. Okay? We generally get a single channel for a call. We have a technology to split it into different speakers here, but we still don't know who each speaker is. We just refer to them as speaker 1, speaker 2, and speaker 3. And the Voiceprint model is supposed to help us understand that Taylor is speaker 1 in the call based on previous calls or some recorded voice and trained Voiceprint model. So we have two phases here. One is to enroll a user to build a Voiceprint model, and the second is to identify a user based on an existing Voiceprint model. how can we do that? The naive approach is just, as Alexa does or Google Home, just ask the user to say a few sentences, repeat them, and we learn to recognize the voice based on that. It works pretty well, but it requires the user to put some effort. Another thing that we can do is maybe get a few calls that Taylor might have been a part of, and ask Taylor to mark in which of these calls she was actually present, and in which of these speakers Taylor actually is. But in Gong, we thought maybe we can do something better without involving the user at all, okay, doing this automatically. We know that Taylor initiated some conversations. We know that she was invited to some of these conversations using email invites. What if we take these conversations, okay, look at the different speakers, and try to identify a speaker that sounds very, very similar in different calls that we know Taylor was part of, okay, and is very different from other speakers in those calls. This would probably, with very high confidence, be Taylor. We don't have to ask Taylor to do anything. We just automatically create a Voiceprint model for her. So in order to do that, we need to select calls of specific user using the metadata we get from the calendar. We try to identify somehow a speaker in each call using some vector to quantify the speaker, and then cluster these speakers together to identify one cluster of very similar speech versus all the other speakers in other conversations. This allows us to scale. We don't need to involve the user. Seems like a better approach. From a research perspective, one way to do this is using a Siamese network. What we do is actually train a neural network to get an audio recording of a single speaker, extract features from that, and get a single vector representation of a low dimension of that speaker in this call. Okay? If we do that twice for two different speakers, eventually we can take the two vectors of extracted features and ask the network to learn to identify if those are the same speaker in different calls or two different speakers completely. Okay? We train the network on a large corpus, and eventually the network learns to identify if two recordings is the same speaker or not. Okay, if we do that for a cluster of, for a collection here of 10 calls, we have 20 speakers. There can be more. We can compute the similarity between each speaker and each other speaker. Okay, in the diagonal we have full similarity, okay, because it's the same speaker. But we can see at the bottom right corner a cluster of different calls, but the same person speaking in them, because the vocal features are very similar. Okay. So what do we do then? We computed the distances. From a machine learning perspective, there are several things that we can do. Okay, several clustering algorithms. This is an unsupervised task. We want to learn how to build the clustering. And then we can say, okay, let's do what they do in those dendrograms of the evolution trees. Take two samples, two vectors, two speakers that are very similar, and join them together. And continue joining more and more similar speakers, the most similar nodes at each time, until we get to the top level. And then we can probably identify a cluster as we would of mammals versus reptiles, for example, and those would be the different speakers. A different approach, let's start with the clustering, run an algorithm called dbScan that each time looks at the neighborhood and says, okay, do I have enough points that are similar to me? If so, I want to expand what I'm doing. If not, I stop and start a new cluster, expand that, and eventually iteratively get to recognize the number of clusters. And here I don't have to have any early hypothesis about the number of speakers. Okay. Another common approach is running the k-means algorithm. Here we just assume that we have here, for example, 5 different speakers, assign a cluster by random. Each cluster is being assigned to the most to the closest samples in our data, and iteratively we run the process again and again until we get to convergence. Okay? We don't have to go deep into those, but these are pretty standard clustering algorithms. We run these in our research based on a lot of data that we have. We know we can get labels on when Taylor actually spoke in each of these or different users, and we come up with the results. And we write our code in Python or whatever. We test different methods, different hyperparameters, and select what works best. Okay, eventually we report those things, and we're very happy. Okay, we've done our research. But in the real world, work pretty much just started. Okay, we have to care about performance, scalability, security, many other things. Okay, to actually get this model to work in a live production system, we need to identify the users that still don't have a model. We need to select which ones we actually run the model on because we have limited resources for actual machine to run. We need to choose which calls to provide to the system. We need to get the wave and metadata to the platform. Okay, we have to save those created models back. We have to do all of those things that seem obvious to probably all of you as software engineers. When I see something like this is my reaction. Okay, so there's like kind of a difference between the way engineering sees the world and research does. Okay, in engineering, the ideal world is the typical classical American family. You want a consistent set of tools. You want to build things once and build them to last. You want a standard system design. You need to take care of all of the other things in the world. And you need to make sure that when you build something, it works. In research, this is the way it looks most of the time. Okay? We want fast food with little preparation. I want to take something from GitHub that seems really cool, just the research that was released 3 days ago. I want to try that. And I want to discard that and not use it again in a matter of minutes. Okay? I want something that looks good in the inside. I don't want to know what's going inside. Okay? If it works, great. If not, not. This is my version of fast food. We need flexibility. We want to be able to quickly try things. And most of the things that we would try are not going to production. Okay? We also do lots of things that eventually, even if it's the same algorithm, shouldn't go into production at all. Evaluation of the model. Okay? I chose this model because it's the best. But all of this analysis isn't really important right now. Okay? All of the plots, all of the things that we do are not really something that you want to have in your production system. So we can ask ourselves, should we tame a data researcher? Should we teach them how to be good software engineers? What we think in Gong that works best is to remember that data scientists are from Mars and software engineers are from Venus. Okay? We come from different worlds, we have different needs, and when we realize that, maybe we can learn how to live together in a better way. What does that mean? It means that we should let each other use the superpowers we have, okay, and not limit and try to tame them. I mean, as a data scientist, which is probably closest to a statistician way back, we were taught to think that the best thing about our job is that we get to play in everyone's backyard. But you see this backyard, it has a big fence, okay? And maybe part of the thing that works best when you're working with the data scientist is to give them the ability to play, but to keep them sandboxed away from the real world in some way. So what do we do in GOG? We want to allow research to quickly adapt code and drop that, use different packages and tools, write a lot of code that should be kept. It is important, okay, for reproducibility, for improving the algorithm, but shouldn't go into production, and play in a safe sandbox, but still write code that is actually used in production and not totally keep them away. And what we adopted is Docker, I assume everyone here is familiar with Docker. And just an interface that means that the processor from the infrastructure and business logic takes care of most of the things that scare us as data scientists. And data science projects performs one mostly algorithmic job in a pretty sandbox environment. So Docker is a great tool. It allows us to contain any code we want pretty much with making use of the full hardware abilities like GPUs. It loads quickly, it stops quickly. We don't have to worry a lot about all of those things. And it allows us to keep in each Docker a totally different environment, different packages, different versions of Python if we need, lots of those things. So a lot of what I'm saying here obviously is related to what we at Gong as a pretty young startup. I mean, 150 employees is not a small startup, but we try to grow fast and move quickly. And we found this way to actually allow us to move quickly. So the sandbox part of this means that we don't get to touch the database. We don't get to go to S3 and bring data, okay? If we need something, engineering knows to bring the file to us in a pretty optimized way, and we work with files. We have a file at a set location that we know we'd read, and our results are written to files, not to database, not to some other position. Engineering knows how to work with these things eventually. And this relates to something that sometimes surprises people. In Gong, we don't use microservices. Okay, and I know that in recent years it's like, you know, blasphemy, and I'm supposed to, you're all supposed to take stones and throw them at me right now, but I'm not the one actually making this decision. I'm just the messenger. And it makes sense in the architecture of Gong in many ways because we don't have small transactions, okay, like in many other aspects. We have big media files of video or audio. Moving those hundreds of megabytes files to a service doesn't make sense. It makes more sense to get a processor, to get a file once, start over there the different Dockers that are already preloaded because the machine is constantly on. In the beginning of the day, it loads, caches all the Docker images locally once it gets them, and works for the entire day with all of this data. And based on this architecture, it actually does make sense to have a better, a more pipeline view of things instead of microservices. So how does this sandbox of research works? We only get to work with files, but we don't have to worry about timeouts, transactions, the efficiency of the SQL query that brings us the data, or database locks, accessing S3 permissions, whatever, okay? We know that when we start something, we get that. Okay, we have the file. When we write the file, we're done. An engineer will take care with the best practices and build ones to last of all of those things. Specifically, just as a side track, we also get saved automatically all the input files that we get, the log of the Docker creation and the outputs that we have in the consoles, and our output. So if there is a bug, we need to understand that. We are able to go and understand what happened in production and fix that, or give our opinion of those things. But we are much more protected from what happens in the outside world. So again, just reiterating, a lot of those things are done by engineering in Java, and all of those things run inside a Docker machine that the Amazon machine runs. Let's skip those things. I've already said most of this. How does it look when we create the Docker? So part of our research project in Gong, releasing code to production, means that we need to create a YAML file that explains how the Docker is supposed to be created. It specifies the pip packages and conda packages of Python. So we actually write Python code. It runs in production, but inside Dockers. We explain what code should be copied. We don't want all code from GitHub to be copied. So we define what we actually do want. If we need files from the code that are not from the Git repo that are not actual code, we need to explicitly specify those, like fixtures for tests or stuff like that. If we need any file from S3, model weights or some other parameters, we also define those, okay? And we define how we expect to be called, both for actually running the algorithm and for running tests. And TeamCity, a build machine, automatically takes this YAML file, reads that, creates a Docker automatically. While doing that, runs the test. What is that? The test. If the test go green, the Docker is created and can be used in the Java machine. Specifically in Java, there's no automatic coupling. So we can push something to master, a Docker will be created, but the Docker gets a tag, and Java decides when they want to make a change by explicitly writing in the code the Docker ID that should be used. So all of this still doesn't mean that as data scientists, we don't have to be good citizens. Okay? We try to actually help in many ways that we can. We're not very happy about that, but we do write code and Python code that actually runs in production, okay? We own the code, we would look into bugs, we write the tests to actually make sure that everything works. I hope I will have time to describe the way we test machine learning models, okay? We do code reviews, and we decide on metrics for monitoring. Java is responsible for reporting these to monitoring services, but still it's the responsibility of the data scientist to say what should be monitored and what is important, and be able to say, okay, is this a bug, is this a problem, and fix issues. But again, this entire method of work is supposed to save us from learning all of the things that we don't really do well as researchers. So a good question recently is, do we actually need researchers? I mean, there are so many cool AutoML tools that beat most of the contenders in Kaggle competitions. And Amazon, Google, Microsoft have cool tools online that allows you to perform all of those tasks. Why do we actually need researchers? It's maybe surprising, but I think most of you that actually work with machine learning models in companies learned to see that. In Gong, all of the models that we work on are created in-house. Just as an example, I know that, you know, everybody, there are so many tools for sentiment analysis over there, but in a sales conversation with an American, the worst thing that they can say to you is, interesting. I mean, doesn't really say anything. Writing our own models gives us significant boost. So a lot of the effort here is actually understanding the question, understanding the best tool, and just trying different techniques, okay, until something really works well. And this requires a lot of training and a lot of work that is not related to software development in the general sense. Still, off-the-shelf solutions are great. They can take you a very long way. We try to use them as well for some of the tasks in the beginning. They allow you to define the interface for working with engineering. They allow you to show something to product pretty quickly on, pretty early on, okay? And explain, this is kind of like what you would get. It would be better, but maybe not a lot better, okay? And probably not different in the way that it looks, in what you can do with that. So I see that I still have a few minutes. I want to quickly go over the way that we test and monitor machine learning models. I haven't seen pretty much anything written about this subject. It took us a lot of trial and error and understanding of what actually needs to be done. And I think that a lot of it comes from the different differences between good software engineering practices and research. I mean, if you'd come to me as a data scientist and told me your model is 100% right, you have no bugs, I would say, no, something is wrong. No model is 100% right. There should be bugs inside my code. But it's a different definition of bug. But when you run your model and it makes a mistake, and it's not working well. It didn't identify Taylor in a certain conversation. Is it a bug? Or it's just a statistical instantiation of the model the way of working? There's a thin line here. And some things are obviously bugs. I mean, if the algorithm just had a memory crash or something like that, we know that these are problems and we need to fix them. In others, it actually takes a lot of time or, a lot of understanding of the actual working of the algorithm to say, nah, sorry, this is a mistake that is just everything worked properly, the model isn't good enough yet. We hope to improve it, but this is part of what we get right now. So it still means that we try to look in those things. The fact that the researchers can look at production code that he wrote, she wrote, and able to understand that helps us mitigate with these things. In many things, we know that understanding deep learning models is very complicated, but if we get a single example, often it's pretty easy to understand what's going on there and compare it to other things. And a lot of time, we actually look into the confidence of the model when doing that. So if our model made a mistake but was very confident about the other, about its own prediction, okay, we would be suspicious. Maybe the actual label is not correct, and maybe our model is making a pretty big mistake here and should be fixed. Okay? In most cases, the vast majority of cases, when there is a mistake, the model is not certain about the true prediction as well, and it's something pretty useful to look at. So how do we actually test our code? We came up with different types of tests: sanity test, model accuracy test, end-to-end test, and statistics test. I'm going to elaborate on these right now. And these are tests that actually go into our build process, and we decide if we successfully create the Docker based on those or not. So sanity test is saying, okay, if I'm failing this test, something is wrong. I mean, I'm taking one instance, but if this test doesn't go green, okay, something is wrong, and I want to stop and look at that. For the image classification, okay, I can put a photo of somebody looking at the camera, and if it's not correctly I recognized as a webcam, I don't care about the overall statistics or whatever. The model has a problem. I want to stop. Probably there is some bug in the process and something is not working properly. So this is a sanity test. Model accuracy test would go on a pretty large set of inputs, okay, with known labels, and we look at the metrics. Now here it's important to know that we're not looking for 100% accuracy. But if we got to 92% F1 score, okay, we want to make sure that when we run a new model, we've made changes, which we change them. We don't want to go below 85%. If we have, there's a problem. There might be some changes, some things that are different, but if there is a large discrepancy over there, something is wrong, stop everything, and have somebody actually manually look into that. End-to-end tests are pretty close to what they sound like. We take calls and try to get them through the machine and make sure that the end result is actually happening and working, okay? That the input is as expected, that we run. We take very long calls. We take calls with no transcript, okay? Because they were, I don't know, just somebody waiting on the line without anything happening, and we want to make sure that they pass, and we want to make sure that we get a valid file that can be read and everything works properly. And the last thing, statistics test. Here what we do is just look at a very large volume of data, very large corpus of data, and look at statistics, okay? If we know, for example, when we're trying to do detection of the punctuation of a sentence, that 7% of sentences are question marks, if we have a change and suddenly it's 20%, something is wrong, okay? We don't really know if the question mark is supposed to be there. We take a large corpus. But if there was a change, is something that requires somebody to look at those things. So it's more soft testing of those things, but the purpose here is to actually allow us to look into things that might have changed and might have been done wrong. So special thanks to everybody that helped, to you for listening. We have a booth outside, and very happy to answer questions after the talk. Thank you.